So today I will teach you regarding the nonlinear blocks in electromechanical systems as well as the frequency response concepts for nonlinear system. Any doubts specifically that I should answer regarding session so far? Okay, let us start. Today we'll be going to the second part of the mathematical modeling of brush type DC torque motor. That is the nonlinear elements in electromechanical actuation system. When you come to nonlinearity, one thing you should understand is in general, in practical, in physical world, all systems are nonlinear. And the linear systems we get only when we approximate or linearize the nonlinear system at certain operating points. You cannot find any systems perfectly linear because as we increase the signal amplitude, definitely it will exceed the range of the physical system. Hence, it is always better to study the nonlinear effects, and if you make something perfectly linear for a given application, that means you are not optimized the system design. You might have done some over design. Otherwise, it will not act like a linear system. For example, if you are making a building, if you are increasing the capacity of the beams and pillars too much, it may act like a linear system with under all operating conditions. But the problem is, under all means all practical operating conditions. But that design will be an over design. You will be using some 5 times more than the steel, 5 times more than cement, etc. So in practice, when we design optimal system, we'll minimize the cost, weight, size, etc. So definitely at some portion of the real operating condition itself, the system will move towards its performance limits or extremes of operation, making the linear system to go to its nonlinear domain of region of operation. That is what we are considering today with respect to an electromechanical actuation system. That is, in general, what is a linear system? Any system which obeys the principle of superposition is called a linear system. Then all other systems are nonlinear. So general definition of nonlinearity is any systems which are not linear are called nonlinear system. Because it is easy to define linear system, it has to obey the principle of superposition, additivity as well as scalability. Both should be valid. That is why practically all physical systems are nonlinear. Now we are considering specific nonlinear elements in electromechanical actuator system. They are, first one is saturation in amplifiers, due to limited power supply voltage or current. Second is plant nonlinearity such as Coulomb friction in ball screw, then stroke limit for linear actuator motion. All these terms are familiar to you. Now we'll consider one by one. Then another thing is the supply voltage limit in power amplifier introduces limit on the motor shaft speed torque characteristics. All these terms I am going to explain in the subsequent slides. I have already sent these lecture notes to Mr. Abhilash, so he will send it to you. Okay. Any doubts so far? No. So let us consider different nonlinearities in electronics part. First one is a simple amplifier. Consider an inverting amplifier using op-amp. You have studied such linear integrated circuits and its gain, assuming this op-amp amplifier as linear, it is minus R2 by R1. That is the voltage gain, output voltage by input voltage. This is the inverting terminal, this is the non-inverting terminal. And we are attaching as a power supply voltage plus VCC and minus VCC here. Okay. But here I have stated it as a linear system. But you know that if the input voltage exceeds certain range, what will happen? The output voltage will go beyond plus VCC or minus VCC. If it was a perfectly linear amplifier, we should have been able to extend this straight line to infinity. But because of the supply voltage limit, the output cannot go beyond plus VCC and cannot go below minus VCC. So you are going to get characteristics like this. This will move like this. So this is called saturation nonlinearity. Saturation nonlinear. This is the simplest nonlinearity that you are studying. Here, superposition theorem, and we cannot add the inputs to get the output as addition, or if we can multiply the input to get the multiplied output once it crosses this nonlinear zone. Okay, this is the simple kind. Then, but for practical purpose, it may not go up to plus VCC and minus VCC. You know that this op-amp is made up of a lot of transistors inside, or some other different types of active devices. And all the active devices require some voltage drop across that device to operate in the specific domain of operation. For example, now we are using the output stage of the op-amps in the linear zone of operation as an amplifier. Hence, the VCE, the collector to emitter voltage of the transistor should be such a way that the transistor will not go to saturation or cutoff domain. So you require a certain voltage drop across the device itself. So you cannot get an output voltage equal to plus VCC or minus VCC. So depending on the particular material, whether it is germanium or silicon-based semiconductor device, there will be a drop. So to be on safe side, if you can assume some 1 or 2 voltage difference. If plus VCC is 15 volt, you can put that cutoff as 13 volt. And if here it is minus VCC, if it is minus 15 volt, you can put the effective saturation limit as minus 13 volt. You don't have to go up to the full range, because after that offset itself, the device will enter into its saturation cutoff zones partially, and hence the linear performance will be affected. Similarly, non-inverting amplifier also we can get only the slope is positive here. The output is limited to plus VCC, minus VCC. One benefit of this simple nonlinear block is there is no memory within this particular circuit. This is pure static circuit because the current value of the present value of the output voltage depends only on the present value of the input voltage. There is no history is not important here. Hence, if you change the direction of the input voltage, the output will trace through the same curve. There is only single curve and hence there is no phase lag, etc. Next block is the integrator block. This is more complicated because it is a dynamical block, dynamic system having storage in the capacitor in the form of charge. We can get the transfer function of this integrator. This is an ideal integrator. It can be obtained like this: V naught T. The output voltage is equal to Q by C, where Q is the charge stored in the capacitor. Here you can see this is zero voltage, minus terminal is on virtual ground. So here also zero voltage. Hence, the output voltage V naught is purely due to the voltage drop across the capacitor, which is obtained like this: Q by C. It is equal to 1 by C. The Q is obtained by integral I dt from 0 to t, or you can get 1 by RC integral 0 to t Vi dt. Assuming here we assume that Q0, the initial value of the charge in the capacitor, is 0. Now, the op-amp goes to saturation cutoff zone prior to V naught cross plus or minus VCC. Hence, this output voltage V naught cannot exceed plus VCC or minus VCC because the op-amp will go to either cutoff or saturation. Hence, the output voltage will be limited. We assume that, as I told earlier, we put a practical limit, say Vs plus Vs and minus Vs as the limit for the VO, which is having a little bit offset compared to VCC. Then what will happen is, that's what I read, Vs is equal to VCC minus 2 volt, just assume. Suppose you give a step command, square wave, it's a square wave command, and I put a inverting amplifier prior to that because this is an inverting integrator. So I put one more integrator at the input side itself to make it as a non-inverting integrator. Then what we'll get is such a, if you give a plus square wave like this, it will integrate as a positive integrator, non-inverting integrator. If there was no saturation, it will go on integrating till the input voltage is positive. The moment the polarity of the input is reversed to minus negative value, then the slope will become just opposite to that. Then again, it will go like this. Here, I have made it in such a way everything is ideal. So whatever is integrated upward, that much will be integrated downward so that it will reach 0, provided the width of positive half and this negative half are same and the values are also equal and opposite. So this is the ideal performance in the absence of saturation limit. The moment you put a saturation limit at the output of the op-amp, what will happen is the moment the output reaches plus Vs, this point, output is reaching plus Vs, then the integration action will be stopped because the transistor cannot now integrate because it is no more in the active zone as an amplifier. Integration action is stopped because we assume here that the op-amp open loop gain is equal to infinity. This will be maintained. not actually infinity very large. This will maintain only if all the active devices inside this op-amp is in linear zone of its operation. If any of that goes to cutoff or saturation, then this amplifier gain that cannot be very large. Ideally, it may go towards zero because incrementally, one of the stages gain will go to zero incrementally, and hence the total gain also incremental gain will go to zero, and the virtual ground concept will fail. And finally, and hence the integration action also will stop. So what will happen is the moment it reaches, it will stop integrating. Stop integrating means the output will remain flat. Okay. And the moment the input comes down, this is the input. Input, once it drops down, then the amplifier comes out of that is saturation zone, and it will start integrating in the opposite direction. So this is the profile. Then again, when it reverses, it will go opposite, and so after 2-3 cycles, things will settle and will come to steady state. But I want to say one thing. There are two ways to add limits to the integrator. One method is as per the real physical happening, what is really happening. The moment the output voltage goes beyond the supply voltage, the integration action is stopped and no more integration and flattens there. But there is one more way you may think equivalently to introduce limit for the integrator. That is nothing but first you use a ideal integrator block of your Simulink. There is an ideal integrator block. Then take the output and put a explicit limit, because saturation nonlinearity block is also available in the Simulink. You put an explicit limit like this. This is called a saturation or limit block followed by ideal integrator. This is ideal integrator, and saturation block is followed. It follows that. But this is not the actual physical integrator with internal limits. Internal limits means that is a reality. Here, the integration itself action should be stopped. That is what I am comparing here. Suppose in the ideal case, we allow the integrator action to follow like this. And if you put a limit outside, what will happen? So if you put as I have shown, you first pass the signal through the ideal integrator, then put an explicit limit. Then what will happen is, first you will get this as the output of the ideal integrator. And when you put an explicit limit, it will get limited like this. And even when the input reverses its polarity, the output continues to remain there, because the output will start dropping only when the ideal integrator output itself is going below the saturation level. But in the actual limited integrator, the inbuilt limit integrator case, the integrator output starts dropping the moment the input reverses the polarity. So in that sense, which is better? But that question is not very.
Simulink mode is better, I think, sir.
I think the second one is better.
Second one is, what do you mean that this one?
Saturation block after
Simulink
the
model.
integrator.
This
Not
one?
the above one.
The above one. This one is better.
So that
No,
is the
sir.
axle integrator, right?
The below one is better.
Below one is better. That is, I will put it as 1 and this as 2. Eh? 1 is better than 2. Why 1 is better than 2?
Sir, because one acts like how it will act in a real situation.
Yeah,
Also,
that is
sir,
what.
like
Yeah.
after some time, we are having an ideal waveform with some offset.
Yeah, so that is correct. See, reality is one only, but still I am just giving a question with respect to system point. Now we are talking with respect to control system point of view. Control system point of view, the performance of two, that is having an additional lag, isn't it? Even when the input changes its polarity, output takes more time to respond to the change of polarity. Really speaking, it should act like an integrator. So if the polarity reverses, definitely it should reflect in the integrator output. Okay, because the rate of change of the integrator, yeah, that is decided by this polarity. But even when polarity reverses, integrator is not responding in the second case. So definitely, first one is the real case is better, and hence we should put limit along with the integrator. Why I am emphasizing this is, if you are really making a hardware integrator, it will behave like case one only. That is the reality. But you can make a software integrator also. Tomorrow you will make a PI controller, and that will be coded as a algorithm. In MATLAB, you are coding it as a discrete equation. You will study digital control and all. So discrete domain, you can simulate it. Then the limit also, it is in your hand. You can put the limit through in software. There you should be very careful. You can give integrator limit in two different ways. One is as it is behaving in the real hardware as case one. Another is a simpler logic. First you simply integrate, get that output of the algorithm, pass it through a limit. That limit logic is simple. But algorithm for one may be more complex, or more effort is required to code it. So, but you should remember one thing. If you code like this number two, it will reduce more phase lag into the system. And while you are getting some benefits of integrator, it will give some disadvantage of the integrator. And this particular disadvantage is known in literature as reset wind up problem of integrator. Reset wind up. Reset wind up. So reset wind up is not a good thing. It will give some some lag effect. Okay, how many of you have driven these modern automobiles with CVT, continuous variable transmission auto gear? Anybody has used that car with CVT? No. Okay. There is a performance called rubber band effect. That is same as this only. That is when you apply acceleration to your accelerator, then it will take some time to respond the gear transmission. After some time only it will respond, but at that time you may not recover the real acceleration. There is a lag effect, just like a rubber it will behave. So all these are reset wind up effects. So even though it looks to be simple, but it is having a lot of practical importance, and I have given a homework here. that is understand the difference between embedded integration limit and saturation block after integration using integration block Simulink. If you go to Simulink, there is integration block, and the integration block is having the facility feature to introduce inbuilt limit, and it has also the feature to initialize the output, the initial condition at time t is equal to 0. All this you can make use of that and study in this particular simulation study. So that is a very important block. The integrator block is a very important block of Simulink, having a lot of features. To study all the features and exercise, and you can apply those features in the PI controller implementation that you are going to study. And the limit of the integrator, you can, for example, the same control loop, you can implement the integrator limit using inbuilt integrator limit as well as an external integrator limit. Take the step response and see the difference. And then you can appreciate the benefit of using inbuilt integrator limit. So this is a very important portion. Go through it, study it well. Any doubts on this explanation?
Yes, sir. I want to know, why did we put the VS as the limit and not VCC itself?
VCC, okay, VCC, say for that purpose, you know the outputs, you have studied the internal structure of op-amp. Have you studied?
At the transistor level, we haven't. We just know the block at block level.
Block level only. Probably there is an output stage for the op-amp. You might have seen stages like this because of this.
The output stage, I think, is a common collector.
There will be different types of configurations will be there. Not to reduce the output impedance very small, as you told, common collector configuration, push-pull mode, it may be used. For example, I am showing one configuration. So this is the output VO, so that you are taking the output from the emitter for one is NPN transistor, one is PNP. So finally, what I want to say is that both these things are working in active domain only, not in saturation or cutoff. If we are using, and here it is plus VCC, for example, plus 15 volt. And if you are assuming that you are taking the maximum voltage as here plus 15 volt, then while this transistor is applying current, what is the drop across this transistor? Then 0 volt only. So definitely, what is the minimum voltage that is required? That is VCE. This is collector emitter. What is the minimum value of VCE which is required to keep this output transistor in the active zone?
VCE saturation.
0.3.
It should not go to VCE sat.
So it's more than that.
It should more than. It should be more than that. VCE sat for silicon, germanium transistor, some 0.2 volt, etc. is there. But we have to use something more than that. It should not because always some bending of curves. So 2 volt need not be required. I am putting on the safe side. It can be even up to 1 volt. Okay, that's also all right. Understood?
Yes, sir. So that 2 volt is just because of this voltage we need to supply, so that it does not go.
Yeah, correct. Similarly, with respect to negative side also.
Okay.
Sir, but we have rail to rail op amps, no sir, which can like very closely achieve VCC.
If you say, if you have it, there is a all device specific thing. I am only sensitizing. You have to subtract some offset. If when you are using a real hardware, suppose tomorrow you are going to implement some amplifier using some available hardware, you should always go to its catalog, see that what is its dynamic range of operation for the output. It will not be equal to plus VCC and minus VCC. Find it out and use it in the simulation. That's all. Okay.
Sir, thank you. Yes.
Yes,
So
sir.
but what if we keep the offset and then give VCC such that it is already offsetted? Like if we need 15 volts as output, then we can give 17 volts or 18 volts.
That is the higher voltage you're telling.
Yes, sir.
Why do you want to use higher voltage? I'm not telling higher voltage. See, offset means it is not positive. Say from positive you are subtracting, and negative side it will be minus VCC, and you are adding that. See, here I am only talking about positive side. Similarly, you have minus VCC. There minus VCC plus 2 volt will come. Okay, that is the minus 13 volt. So plus 13 to minus 13 volt. That's what I understand. Mean.
Okay, sir.
Okay, okay. Okay, can I go to the next portion? That is the implicit limit on motor speed torque output due to power amplifier supply voltage. This is, we are going into the system dynamics also. Dynamics means the motor part also, along with the, so not only pure electronics part, it is electronics plus motor portion. Recall the previous block diagram that we used, that is for armature controlled brush type DC torque motor, and we are supplying a voltage EA at the armature terminal, and back EMF voltage is coming. In the armature circuit, we are subtracting KB into omega M. That is a back EMF from EA, and the resulting voltage only is dropped across the armature resistance RA, producing a current IA multiplied by KT will give TM. Okay, this is what. Now, just like as we discussed, the power amplifier, assuming it as a linear amplifier, definitely there is a plus and minus voltage limits, plus Vs and minus Vs, beyond which you cannot increase EA. So even though you are increasing EA beyond that, the output voltage cannot exceed plus Vs or minus Vs. Accordingly, the speed torque characteristics of the motor, the top limit, performance limit corresponds to Vs KT by Ra as the stall torque and Vs by Kb as the no load speed. Similarly, on the other side, negative side, we have minus Vs KT by Ra as the stall torque and minus Vs by Kb as the no load speed. Hence, motor point of view, your speed torque characteristics will be lines parallel to these two lines and lying within these two boundaries. That's what I have hatched it. This is the case with respect to generating point of view. Now, with respect to consuming point of view, that is mechanical side, there is a speed torque requirement. How we can plot it, that's what I am going to show. That is source side, you can write Tm, motor torque developed, basically EA into KT by Ra minus KT KB omega. KT is there in the both case. So this is the expression, and this is what we have plotted. Tm along y-axis and omega m along x-axis. And if you take omega m as the independent variable, you can plot Tm versus omega m for different values of the supply voltage at the so-called EA, which will vary based on the applied external voltage. Okay. Now on load side, we can write Tm equals J equivalent theta m double dot plus B equivalent theta m dot. This is the final expression that we had derived, even including the effect of gear transmission coupling, motor internal moment of inertia, load moment of inertia, etc. Suppose that from user point of view. For example, if you consider gimballing of a rocket engine, we want that the engine should be gimballed along a sinusoidal profile, because sinusoidal profile always acts like a typical profile. We can attach maximum deflection range and the frequency parameters to that. Suppose theta m is the maximum deflection range and omega is the frequency. One typical example is many of the launch vehicle nozzles. We would like to deflect with a plus or minus 5 degree amplitude and a frequency corresponding to some 5 hertz. And normally, even though amplitude is 5 degree and frequency of operation is 5 hertz, there is a correlation between them. 5 plus or minus 5 degree is the maximum amplitude. So we will not deflect the engine by for this maximum amplitude with the maximum frequency. That will not do. For example, we'll apply the maximum frequency of 5 hertz only for 0.5 degree, 10%. When you make it 20%, you'll further reduce like that. So that is what I am going to show here. So there is a special frequency amplitude pair through which only you will deflect or steer the engine or the load. Theta mt, you can say it is equal to capital theta m into sine omega t, and we give specific values for theta m maximum and omega, so that the load dynamics will do the intended purpose. If that is the trajectory theta mt, you can differentiate to get theta m dot and double differentiate to get theta m double dot. And these are the formulas. Then you can calculate what is the required Tm, torque required at the driving. That is how much torque should be generated by the motor to steer the equivalent load dynamics, including internal and load, through a sinusoidal profile like this with a maximum amplitude, that is the amplitude of capital theta and a frequency of omega. Then you can make a table like this: time t, theta m dot, theta m double dot, and tm. Vary this time t from 0 to some 10 seconds, for example, in steps of 1 millisecond. Find all these things. After finding all these things, you can forget about other columns. So only worry about theta m dot and tm. That is while this load is steered along this trajectory, theta m omega t, there will be an associated profile for motor velocity and motor torque that you simply plot in the same graph. Because here also it's omega m, and you don't confuse with this omega m and omega. Omega m, here it is the speed of motor, that is same as theta m dot. That is what I have written here. Theta m dot is same as omega m, where omega is the frequency of operation. It is not simply the angular velocity, it is the frequency of the signal. Thus, theta m dot is same as omega m, and hence you can plot this theta m dot, this data, along this axis. At Tm, it is the torque developed by the motor. So you can very much plot in this along this axis. So finally, both these curves should match. Consider this curve. This is and if you pass it through a sinusoidal, you will get a closed contour. You cannot say what exactly is the shape of this, but it will be a closed contour. And this curve, the speed torque requirement from the load side, it should be well within the speed torque capability of the motor. If it is so, that is speed torque requirement of the load, if it is not touching the extreme limits of the speed torque boundaries of the motor, given these are the two boundaries, if this is not touching, then what does it mean is the motor is able to deliver this speed torque combination without touching any nonlinear limits. But the moment the requirement is, suppose it is like this, because if you substitute, these are all linear, there is no nonlinear, parameters are constant. Definitely you are supposed to get a smooth curve like this. But what will happen is the requirement exceeds the motor capacity. So motor cannot deliver that. Suddenly it will get chopped. So if it is moving like this, the moment it touches the motor limit, then the curve will pass through this only, traverse through this upper boundary speed torque limit again. Once it is inside, it will come back, and then again it will traverse through the boundary here, and so on. Here you can see the motor nonlinearity comes into play. There is a speed torque limit of the motor affect the performance. And this is what I want to say. There is an implicit limit on the motor speed torque output due to power amplifier supply voltage. The basic cause for this speed torque limit is nothing but this power amplifier supply voltage. There is no other mechanism which detect the speed and put limit like this. This is, if you simply simulate this, you will get this as the characteristics. But it is not that direct as we have seen in the simple amplifier saturation. So you should understand this clearly, how this works. I hope you got this point. That is what I have written.
So can you please explain how we got that red color curve once again?
This curve? Or this
No,
curve?
sir. The curve. No, yes, that curve, sir. Yeah.
This one.
Yes, sir.
Say, you understood this equation, Tm is equal to this,
Yeah.
there is no doubt. There is no doubt. Up to this, there is no problem.
No, sir. Yeah.
And you can form this table also, no problem. Agreed?
Okay, sir.
This is nothing but we are simply substituting time and getting theta m dot as well as Tm.
Okay, so we are
this is-
plotting point by point. Is it like that, sir? We are plotting
Yeah,
point by point.
Exact,
Okay.
except point by point. And
Okay.
if the point is, this is actually, we are plotting the load dynamics characteristics. We are for a, here, if I put the independent variable as theta m dot, omega m is same as theta m dot, I told you. For a given theta m dot, and while we are passing through such a sinusoidal profile of motion, what is the torque required? That is nothing but the inverse dynamics of the load. Inverse dynamics of load. Okay.
Sir, the last column is a torque, right, sir? The TM.
Last column is torque, Tm. Tm is same as capital Tm. The same as capital Tm.
Yeah, okay, sir.
Sir, but if the theta m were to vary in a very slow, then it would have been the same curve, like parallel to the motor speed torque characteristics, right?
Yeah, slowly then what you have to do is either you have to reduce the this one, the maximum deflection, or you vary the frequency. Then the variation will become slower. Okay. What you mean is reducing the frequency. Instead of 5 hertz, it can be 0.5 hertz, 0.05 hertz, like that.
No, sir. What I mean is that earlier on, when we saw this diagram, you had drawn the speed torque characteristics parallel to the the limits, even for the load side. That is for
Okay.
what kind of?
Okay. Yeah. See that I am drawing the source characteristics. Yeah. See, if I plot this, there are two parts for this. One is the source side. I have written here. Tm is equal to Ea into Kt by Ra minus Kt Kb by Ra into omega n. Okay.
Yes, sir.
For source side, what you are doing is you, for a given Ea, you are varying omega m, getting the value of Tm. Then you change Ea to another value. For different values of Ea, you will get different parallel lines. Okay. This is nothing but the source character. Source here means the action of the motor to convert electrical energy to mechanical energy. That is the source I mean. Okay.
Yes, sir.
Now what I am plotting is the load side. That is the inverse dynamics characteristics of the load. Okay. So both are different. Here there is no differential equations at all. Here you see dynamics comes here. That is why it goes in a curve and etc. Here it is purely static. There is no presence of curve here. If you reverse also, it will track the same line. But it is not the case here because it is a dynamics equations are there, and because of that, when you pass through a curved profile, there is reversing. It will not come through the same line. That is why it goes as a circle. I will call it as a closed contour. It is not even ellipse, something like that. Understand? That is this dotted line. Now you are mixing these two together. We are constraining, we are coupling a load with a constrained source. When they combine together, they have to, because finally the consumed torque cannot exceed the generated torque. Okay. As long as the consumed torque is less than the generated torque, then automatically the generated torque will be equal to consumed torque. There will be only single curve. The moment the consumed torque exceeds the generator capacity for the torque, definitely it will be constrained to follow the generator limit. That is why it is traversing through this limit.
Thank you, sir.
Okay. All right.
Sir, what will happen to the unused torque? I mean, the difference.
There is no difference. Say to every action, there is an equal and opposite reaction. It is always generated is equal to consumed. That's what I told. Here, there is no difference. Here, only we are telling with respect, we are comparing with respect to the performance limit maximum that we can get out of the system. Here, this much only is required, and the system is having this much of capability. So we will use only what is required. But here, this dotted line, this much is required, but this is the only capability. So you cannot go beyond the capability. It has to get limited. The moment it is get limited means this is, I am calling as the non-linear operation. That is, the linear system will go into the non-linear mode. Exactly at the same instant, the voltage here, that will be limited. They will go to the limit. Okay. And the moment it enter into this point, that point will exactly coincide with here the command goes in this limit. Both will be at exactly correct. And this will go to the speed torque domain. Say tomorrow you are going to implement this in the Simulink block, and you are going to tap the output, and you yourself is going to plot and see that you are going to get these characteristics. Then everything is crystal clear in the simulation block, you yourself will be understanding how it is happening. I know that sometimes now you may have some confusion, but there exactly the simulation helps you to understand things. Every signal is transparent there. You can plot. If you question something, directly you can question the variable in the simulation block. Go and tap and plot and see whether it is logical to your brain understanding. Then you will understand each and every corners of this particular graph. Okay. Even then you are not getting, then again we'll discuss. Okay. All right.
So this curve is only when we consider the theta output which we want as a sinusoidal profile, right? Otherwise we can get any form. It's just that expression, it is limited by the supply voltage, as you said.
Yeah, it need not be, say, if you change instead of sinusoidal profile, some other profile, but still it is a periodic form. Then instead of such a contour, the contour shape can be some other contour shape, but again it will be limited when it touch the upper bound. And again, some other contour will come here, and then, and in all cases, you cannot exceed this speed or bound. That's all. You may be dancing within this two bounds only. Okay.
Yes, sir.
Okay. Next one is actuator stroke limit. This actuator stroke limit looks to be very simple, straight sometimes. That is, you may think that it is similar to the saturation limit of amplifier. To be in general, I have given two stroke limit. Stroke limit is nothing but if you have a motor. Motor normally rotates indefinitely in positive direction, negative direction. But when you couple it with a load in position control system, load normally will not rotate full. For example, an antenna orientation control. You know that this parabolic dish antenna will be there and it will mounted on some surface. Always, if this is the center line of the antenna, it can maximum or in some plus or minus some 30 degree, plus 30 or minus 30. Because you are attaching some motor mechanism, some bracket, so many things will be there. It will not allow it to rotate indefinitely like a motor. So there is always a the maximum limit, positive limit and negative limit for the deflection. This is a rotary case. If it is a linear movement case, definitely there will be a plus linear displacement limit and minus displacement limit will be there. That is what we represent here by the limit on theta L max and theta L minimum. And here the slope is equal to 1 because the input deflection is the actual shaft deflection. That is unlimited shaft deflection that I am representing by integral of theta L dot, because integral of theta L dot is nothing but theta L. Why I tell the integral of theta L dot, the real, if you see the cause effect sequence, we are actually connecting an actuator. Actuator applies torque on the load. Torque will produce acceleration theta L double dot. That on integration you will get theta L dot. On further integration you will get theta L. So theta L as such is not directly coming. It is coming after integrating the angular velocity. That's what I put like this. Strict mathematical terms you have to write theta L at time t is equal to 0 plus integral t0 to t theta L dot dt. Okay. So finally, what I'm telling is there is a dynamics associated with actuator stroke limit. The dynamics is nothing but the integration of acceleration to generate velocity and integration of velocity to give deflection. But in your amplifier, there was no dynamics. Inverting amplifier and non-inverting amplifier, you are giving an input voltage, you are getting output voltage. There, Ohm's law only plays there, which is a so-called static law, not a dynamical law taking care of derivatives and all. So here, finally, outcome is the output cannot exceed plus theta L max and minus theta L max. But the actuator stroke limit is something more than that. What the meaning is, the implementation of the actual physics during stroke limit is more complex. That is, when the load shaft press against the kinematic limits, plus theta L max or theta L minimum, then theta L dot should be forced to zero, right? The moment it hits the limit means the velocity is going to, it is forced to zero. But in simulation, you have to do that. Further, the logic should have provision to return to the linear operating zone once theta L double dot reverses its polarity. So we will implement this in some subsequent class, but now we will assume the simple logic, that is just a saturation block of the simulink we will use and put at the output of the theta L to limit it to some value. But actually, the moment theta L cross the limits, we have to have a logic to force theta L dot to zero, and theta L double dot also will be zero. How this happens, you know, when it press against the stroke limit, the full applied force or torque will be balanced against the reaction force or reaction torque you are getting from the mechanical stops. So up to that level you have to go. And truly speaking, when it goes and hit the stroke limit, there is another something called impact dynamics also will be there. It is not a simple thing. Then that impact dynamics, if you want to model, you should model the contact stiffness. There is a term called coefficient of restitution. It will bombard back, or perfectly elastic collision, or perfectly inelastic collision, or damped collision. So there is no end of it. What I'm telling is, if you are really modeling a real physical process, depending on the importance of the process, you have to capture all such physical what is happen phenomena and model it mathematically. Then only the model will be correct. But to start with, we will approximate with a reduced order model, even with respect to non-linearities like this, and proceed, and one by one we will increase the complexity. So tomorrow